In problem 1 of discussion 3, we're going to be doing some more linear algebra review. And so the main thing that pertains to this problem in particular is the spectral theorem. Keep in mind that we did talk about the spectral theorem in last week's discussion. So if you want a more in-depth and thorough explanation, I encourage you to look back at discussion 2's videos. But I also give like a quick overview here, just as a quick reminder of what the spectral theorem says. So the spectral theorem says that given that A is an n times n square matrix of real numbers, here's our square matrix, we know that A is symmetric if and only if A is orthogonally diagonalizable. And so, if A is symmetric, then the following holds. We can basically break down A into 3 matrices. So we can decompose it into this matrix multiplication of the form Q dQ transpose, where Q is an orthogonal matrix that consists of an orthonormal basis of eigenvectors. And D, this matrix in the middle, is a diagonal matrix of eigenvalues. Okay, that was quick. Again, if you want more in-depth stuff about this, then definitely look at discussion 2. Otherwise, we'll jump directly into the question. So here we are given that a symmetric matrix, sigma, is of dimensions n times n, and it is positive definite if for all x of vector form 1 or x1, x2, dot, dot, dot to xn, such that x is not equal to 0, we have this property. So if we have a symmetric matrix and it's positive definite, then this property holds. Another thing that I want to know is what positive definite means. So the definition of positive definite is that all the eigenvalues of this matrix are strictly positive. So that's going to be really important. Okay, and so we want to show that sigma is positive definite if and only if there exists an invertible matrix A such that sigma equals A transpose. And so whenever we see if and only if, we know we have to prove this in 2 ways or in 2 directions. So the normal way and then the converse. And so let's start by proving it the first direction, which is if this matrix is positive definite, then we want to show that there exists, and I think this is a there exists symbol, there exists an invertible matrix A such that the sigma is equal to A times A transpose. Okay, and so we know that this sigma is positive definite, which basically means that all the eigenvalues of this matrix are strictly positive. And we also know that this matrix is a symmetric matrix. And so first, we can look at the spectral theorem. Remember that the spectral theorem says that we can break down any symmetric matrix into this decomposition, where we have an orthogonal matrix times a diagonal matrix of eigenvalues times the orthogonal matrix transposed. And so I'm going to break this matrix down into exactly that, Q, D, Q transpose, where this is, right over here, is the matrix of eigenvalues. And because this matrix is positive definite, we also know that all these eigenvalues are greater than 0. Okay, and this is just some arbitrary, or not arbitrary, this is an orthogonal matrix that consists of an orthonormal basis of eigenvectors. Okay, and so what I'm going to do here is we want to somehow turn this into this. And we can also write this D out. So let's let D be equal to this matrix of eigenvalues, lambda 1, lambda 2, dot, 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 all the way to lambda n. And remember, all of these values are greater than 0. And so if I can turn, so Q and Q transpose, I guess, they almost look like this shape. But if I can break down this D somehow, such that it also fits this format, then we would have proven this first part. And so since all these eigenvalues are greater than 0, we can take the square root of them, right, and not have a problem. And so let's have some matrix B equal to the square root of all of these, or the diagonal matrix that consists of the square root of all these eigenvalues. Notice B times B transpose, which B transpose is basically itself, because if you transpose this, it's literally just itself. And if you multiply this by itself, you'll notice that you multiply the square roots by each other and they form this D. So we can say that D is equivalent to B times B transpose. And now we can just replace this D and this equation into over here. And so I'm going to do exactly that. I'm going to say this matrix is equal to Q times B transpose times Q transpose. And this is equivalent to QB times B transpose, Q transpose. And notice something interesting. Here, if I write it like that. Oops. Why did I do that? Oh, okay. Notice how this right over here is equivalent to the transpose of that, right? Because QB transpose is equivalent to B transpose Q transpose, because the transpose basically distributes and the matrices get flipped. And so we can write that this is equivalent to QB times QB transpose. And this is exactly this AA transpose format that we were looking for. And therefore, we have proven this first statement right here. If this matrix is positive definite, there exists an invertible matrix such that we can write this as sigma is equal to A times A transpose. And we know that A, which is equal to QB, is invertible, which is what it asks for, right? It wants A to be invertible. And we know that that is the case because Q is invertible, since it's an orthonormal basis, and B is invertible since it's just this diagonal matrix. And so if both matrices are invertible, then the product of those two are also invertible. Okay. And secondly, we need to prove the opposite, which is we need to prove that the converse is true. That if there exists an invertible matrix A of this dimension n times n, such that we have this to be true, then we can show that this matrix is positive definite. And so this approach is going to be slightly different. So we want to show that this sigma is positive definite. In our problem, we are given that a matrix is positive definite if for all x, such that x is not equal to 0, we have this to be true. And what that is basically saying is positive definite is equivalent to saying that x transpose sigma x is greater than 0 for x not equal to 0. And this is given, right? Given from problem. So if we can show that this equation is true, then we can show that this matrix is positive definite. And so let's do exactly that. Okay, and so we have x transpose this matrix times x, and we can replace this matrix with A transpose, and so that gives us x transpose A transpose x. And again, notice how these are basically almost the same, except they're transposes of each other. X transpose A, you take the transpose of this is equivalent to A transpose X. And so we are going to say that we're going to replace this with A transpose X transpose, and then the latter stays the same. And notice how we're multiplying basically some, vector, let's say we have vector B transpose and we're multiplying it by itself. So this is equivalent to the norm, the square norm. And so we can write this as equivalent to A transpose X, and it's the square norm of this. And notice how the square norm means that this must always be, the square norm always must be greater than or equal to 0, but in our case, it's actually strictly greater than 0. And the reason we know that is because since A is invertible, right? We're given that there exists an invertible matrix A. We also know A transpose is invertible. And we also know X is not equal to 0 because that's given to us from the problem, right? We're told that such that X is not equal to 0, that this is true. And so A transpose times X must not be equal to 0, because if this matrix is invertible and this vector is not equal to 0, then we can't have the product of them be 0, because otherwise AT would not be invertible. And so because this cannot be equal to 0, this cannot be equal to 0, so this norm, the square norm, can't be equal to 0, so it must be greater than 0. And thus we have shown that given we have these properties, some invertible matrix A, the square matrix A, such that this holds true, we have shown that X transpose times this matrix times X is greater than 0. And because we have shown this, we have therefore proved that this sigma matrix is positive definite. And that concludes our proof for question 1. So I'll see y'all in question 2.